Hello, everyone. We are from RoboK. We're a company focusing on automotive ADAS applications and cost-effective platforms, mainly on computer vision algorithms. Today, we're glad to be here to share some of our work in localization, running on edge devices, using ARM-based computation platforms. We will be talking about how different sensors can help solve localization problems and some of the optimization works we have done for embedded devices. So first of all, what is localization? It is basically knowing where you are. Technically, the system of moving hardware needs to know its position in certain coordinate system. Sometimes it needs to know its pose as well. But why do we care? So the killer application of localization for our daily life would be navigation. So we are relying on our mobile phones and in-car GPS navigation systems to tell us where we are and how far it is to our destination. The localization is also one of the crucial components in many applications. Either delivery robots or autonomous vehicles need to know where they are as the first step in order to complete any tasks. Some safety-critical tasks like lane assistant for driving assistance requires decimeter or even centimeter level accuracy, whereas some just need meter level, such as running apps on your phone or wearable devices. Therefore, different localization solutions consist of different hardware and software. Localization systems do not always work, just like any other systems, our internet, for example. For most applications, GNSS is the main sensor to solve localization problems. It works very well when you have clear view of the sky. This is because the GNSS chips require a couple of satellites to calculate its coordinates. Some advanced GNSS solutions like the RTK GPS can achieve centimeter level accuracy. There are obviously limitations of GNSS-based solutions, and for some applications, these corner cases are not uncommon to encounter. And probably every one of us has experienced the location drifts and signal loss when driving downtown or underground parking lots. So what are the alternatives when we do not have GPS signals? We will talk about sensor types that can provide accurate localization results on their own robustly in most conditions. Hence, we will skip sensors like wheel odometry, IMU, etc., where the error will accumulate much faster, but they can always be used as a supplementary sensor, which we will cover later. So first of all, most new cars are equipped with at least one camera, and a continuous image string can be used to calculate the relative position and pose changes between frames. It is called the visual odometry. A typical approach would be tracking a subset of points in the image. There are many ways to define the subset of points we call key points to track. One of the criteria is that they tend to be unique across frames and easier to identify. We will talk more about vision-based localization in later slides. And second and most popular nowadays is with the wide application of the LiDAR in autonomous driving. So LiDAR-based localization systems have developed rapidly and has become a hot topic of research recently because LiDAR produces very precise 3D scans of the environment in real time, and one can calculate the motions between two consecutive scans by matching the 3D points. However, as you can see from the left image, LiDAR can have its limitations, and so does the camera and many other sensors. We have conducted some benchmark work. We compared 4 popular sensors that are used a lot in localization solutions. As you can see, different sensors have pros and cons. GNSS suffers from poor signal or even signal loss, but it can work perfectly in an open space environment. One can get very accurate localization information by upgrading the GNSS to, for example, the RTK GPS, and is relatively cheap. Camera sensors struggled to deal with lighting changes, motion blurs, and most importantly, it needs more complex processing to derive the motions. But cameras are cheap and provide rich contextual information for higher level applications. As you can expect, LiDAR is the most accurate sensor, but bad weather conditions will interfere with the active light pulses from LiDAR, and hence make it impossible to work in rain or snow. And LiDAR is very expensive. Last but not least, the inertial measurement unit, IMU. It consists of an accelerometer and gyroscope, which provides linear acceleration and rotational velocity. It is used as a complement for another sensor type, for example, camera or LiDAR. Due to the nature of it, environmental change, like temperature change, can introduce noises to the measurements. Hence, there are high-end IMUs to correct those noises automatically. As a consequence, there's a price tag to it. So the price of IMUs can vary vastly, ranging from $5 to $2,000. We found that a medium-priced IMU can work very well and as a perfect aid for other main sensor types. So, to achieve a robust localization solution, working outdoor and indoor seamlessly, we need to fuse multiple sensor types to compensate each other. And most importantly, we need to maintain the cost efficiency and competitiveness of the product. GNSS is still the go-to sensor for an open environment. When GNSS signal is bad, we have other two sensors to help, camera and IMU. We RoboK specialize in computer vision tasks, so we choose the camera as the main sensor for localization, and then we fuse IMU to compensate the poor vision situations. Now I will hand over to Duncan, our computer vision expert in RoboK, to talk about some of our findings.
Thank you, Lee. I will be going into more detail about vision-based localization approaches, as well as our vision and sensor fusion-based approach. So first, I will give a quick overview of how different vision-based localization algorithms work. We can put these different approaches into three categories. There's your feature-based approaches, your direct methods, and your semi-direct methods. So features. Lee briefly went through the feature-based localization concept in the introduction. So essentially the process here is you first try to find a small number of key locations within an image, say 100 points. 100 is quite small. Then we examine a square patch around each key location. We then represent that small patch in a simpler and lower dimensional representation. The key is to find a representation that is lighting invariant. For example, counting the number of the directions of the edges within each patch, similar to the famous SIFT method. This is more robust and more discriminative than just using the raw pixel values. This lower dimensional representation of a patch is called a feature. We then track these features by trying to match them between successive frames. Once we have compiled a list of matching features, we then see how they have moved between successive frames. With these movements of the features, we can then triangulate our own movement. Okay, so direct method. Direct methods don't use features. They don't do much image processing on the image for that matter. Features are quite heavy on the image processing and are relatively quite expensive to compute. As a computationally cheap approach, direct methods just try to perform the triangulation on the movement of the raw pixel values themselves. Okay, and semi-direct method. Wouldn't it be good if there was an in-between method between features and direct? Semi-direct methods can be viewed as a hybrid method, partially using features or just a less complicated representation of the image, such as performing edge detection on the image. So one example framework would be to just use features to initialize the tracking, then use the computationally cheap lower-level image processing to perform the tracking on. Edges are a good trade-off between cheap and robust. So limitations with vision-based methods. The real world is not perfect, and you are prone to receiving poor quality images from your sensors from time to time, such as when the sun is shining directly on your camera. Those images tend to look quite nasty. You can get large shadows, And also you can get motion blurring, i.e. the image could be blurred, such as in the given example in this slide. A major drawback with using vision only is the scale uncertainty. You can perform the triangulations between frames to work out the distance travelled, but they won't necessarily be in meters. With a monocular camera, well, single camera, the problem is not constrained to handle scale. But one can add an IMU sensor to constrain it and introduce proper scale. So talking about using extra sensors brings us nicely onto our architecture and system. So we have three sensors: a single camera, an IMU. An IMU measures acceleration and rotational velocity, and a GPS. We perform some processing on the incoming mono camera and IMU readings. On the camera side, this includes extracting both high-level and low-level features from the image, which includes the features we mentioned earlier. On the IMU, this includes bias correction, a computationally cheap way to account for an ever-changing bias in the IMU sensor is to pre-integrate the acceleration and rotational velocity readings from the IMU. Then these three processed sensor readings get agglomerated together into a fitness function. And then an optimizer is used on that. In many cases, a least squares optimizer will do the job. The sample weights for each sensor is different. So, for example, an IMU sensor would have 10 times the frames per second that the camera would. So it is possible to perform more frequent pose estimations on the separate, faster or independent sensors. A final fused pose is given by either the pose predicted by the optimizer, which took all sensor readings, or an updated fused result from the partial sensor readings. Okay, so we now move on to talk about experiments and benchmarking, as well as covering edge cases. Okay, so in this benchmark, we ran localization algorithms on a public indoor dataset. Quite a famous one by ETH Zurich called the RoDOK dataset. This dataset involved a drone moving around an indoor environment, which was a hallway full of heavy machinery. It came supplied with an IMU and sensor readings on that drone, as well as a target ground truth movement trajectory. That target ground truth movement trajectory was derived by putting a prism on that drone and using lasers to essentially calculate the location of that drone. That was incredibly accurate and was used as ground truth. And overall, this dataset has been used in lots of academic evaluations. So we ran a feature-based algorithm, OrbSlam2, on this dataset and achieved some fairly good error rates between the feature-based algorithm's prediction and the ground truth. So we got errors ranging between 3 centimeters to 6 centimeters. It had an FPS of 10 FPS on a quad-core A73. Although the error rate here looks quite good, the output was unscaled, i.e. used information from the ground truth to help scale it up into meters or centimeters. We run a direct method, LSD-SLAM, on the same dataset. In our evaluations, it did not perform as well, getting 46 centimeter error and then losing track in the medium and difficult sequences. But it did achieve 14 frames per second, so it was faster than the feature-based method. Okay, we also ran a semi-direct method, SVO2, on the RoDOK dataset. It achieved errors of between 48 and 63 centimeters. The frame rate, however, was much better at 35 frames per second, faster than the feature-based method. Therefore, we can use a hybrid feature-based and semi-direct method to achieve a balance of speed and accuracy. So here we have a video regarding an edge case scenario for the car application. So sometimes you won't have GPS readings. One example is when a car enters an indoor car park. We gathered a data set which involved a car driving around a corner and then entering a car park in Cambridge. When it enters the car park, the GPS signal is cut off. We still have the vision sensor turned on and it is still tracking. And as you can see here, we have gone underground, and we still have the feature, and we're still detecting features, and we are still tracking and estimating a trajectory underground with no GPS. Okay, we are still underground and still tracking. Yeah. So we will turn round one more corner and then still track, and then that will be the end of the sequence. Okay, so let's analyze what just happened. So we had a GPS signal up until we entered the car park. That is represented by the green line in the graph. The pink line in the graph is the tracking from the vision sensor only. And as we can see, the GPS, or the green line, cuts off after we've passed the corner and before we went into the car park, but the vision pink line still carries on. So I will hand back to Lee to talk about the optimizations that can be applied to the localization algorithms.
At RoboK, we apply a pipeline of optimizations for many computer vision tasks. So some are software level vectorization, some are hardware specific. I'm going to focus on hardware specific here. So many CPUs have the so-called vector or SIMD, single instruction, multiple data instruction sets, so which apply the same operation to multiple data elements of the same type and size. Basically in a single vector, and you process them simultaneously. So ARM CPUs have NEOM instruction set. So we show some benchmarks using the ARM V8 CPU. We're looking at 128-bit registers, which means we can have up to 4 times speed up if we use the NEOM instruction set for all floating point operations. So there are some operations in image feature extraction that can be vectorized. For example, in this graph here, we use edges to track motions, and edge detection is a perfect candidate for vectorization. So we compared the speed of SOBO method and Kenny method based edge detection using NEOM implementation. So both methods are implemented in X and Y directions. So the first 2 graphs are for SOBO, and the second 2 bars are for Kenny methods. So we vectorized all possible loops and used a 1080p image for testing, and we achieved a bit more than 2 times speed up. So the same method, actually, you can see here, has been applied to other parallelizable components in our system. During our experiment, we also have encountered some other challenges while testing our localization module. First of all, we need to thoroughly evaluate our system. Apart from normal driving scenarios, we need to test the robustness of our solution in various corner cases, like tunnels, poor light conditions, different driving speed, etc. And we have to build a full regression database according to industry application requirement. And the second one is very practical. Again, a good sensor fusion results really rely a lot on closely timestamped sensor measurement. However, many sensors, almost all cameras, just timestamp their data on arrival of the companion computation platform. For most cameras, this creates 5 milliseconds to 40 milliseconds latency, and there's no way to find out the exact time when the measurements were taken for different sensors. So we used hardware synchronization to achieve sub-milliseconds level timestamp difference. So we collect our sensor data with synchronization at more than 20 frames per second for all sensor. So with an efficient localization solution on edge, more complicated higher level functionalities can be achieved. We can take a modular approach to autonomous driving. So OEMs and tier ones can do hardware and software upgrades separately. One OEM can start with perception modules as visual aids, and then later upgrade to sensors to work with localization software. and eventually migrate to full autonomy by adding full vehicle control. The scalable design delivers a bottom-up approach for different OEMs. Another hot research areas can change the landscape of the localization. So as computer vision remains the killer app of deep learning, some functionalities like depth prediction can be used as a tracking source. So the RoboK way here is in active research in this area and has achieved a top-ranking depth prediction and real-time performance on embedded devices. We hope to see robust localization running on all the edge devices in the future applications, and hopefully in daily life as well. That is all for our presentation. Thanks for watching. Feel free to leave any questions.